On October 9, 2022, a wave of radiation hit Earth so powerful that it temporarily altered the chemistry of our atmosphere, and the explosion that caused it happened 2.4 billion years ago. This wasn't a supernova. It wasn't a solar flare. It was something far more violent. Astronomers call it GRB 221009A, and it was the brightest thing we have ever recorded in the history of human observation. In just a few seconds, it released more energy than our sun will produce in its entire 10 billion year lifetime. The question is, what could possibly do this? And why did it point directly at us? For decades, we thought we understood cosmic explosions. A star runs out of fuel, gravity wins, the core collapses. Boom, supernova. These events are spectacular. They outshine entire galaxies for weeks. They forge heavy elements like gold and uranium. We had equations. We had models. We felt comfortable. Think of it like understanding car crashes. You know the physics. You can predict the damage. Then someone shows you a crash that vaporized not just the car, but the entire highway, the city around it, and left a crater visible from space. That's what GRB 221009A did to our understanding. When the data came in, astronomers thought their instruments were broken. The readings were impossible. Satellites designed to detect nuclear explosions. Saturated, X-ray telescopes, overwhelmed. Even the Earth's ionosphere, the layer of charged particles 50 miles above your head, showed the impact. This wasn't just bright. It was the kind of bright that made physicists quietly close their office doors and recalculate everything. And then they found something nobody expected. Here's what actually happens during a gamma ray burst. A massive star, at least 20 times heavier than our sun, reaches the end of its life. But instead of a normal supernova, the core doesn't just collapse into a neutron star. It keeps collapsing, past the neutron star phase, past anything that can stop it. A black hole forms in milliseconds, but here's the twist. The outer layers of the star are still falling inward. They slam into this newborn black hole and form a superheated disk spinning at nearly light speed. Magnetic fields twist, pressure builds. Then, two jets of pure energy punch through the star's poles like bullets through tissue paper. Those jets contain particles accelerated to 99.9999% the speed of light. Now here's the number that breaks your intuition. In roughly 10 seconds, this event released 18 tera-electronvolts of energy in gamma rays alone. For comparison, the Large Hadron Collider, humanity's most powerful particle accelerator, operates at 6.5 tera-electronvolts. This dead star outperformed our best technology by nearly triple, and it did it from 2.4 billion light-years away, which leads to the part that most people never hear about. GRB 221009A wasn't just powerful, it was pointed directly at Earth. The jets from gamma ray bursts are narrow, only a few degrees wide. The odds of one this powerful aiming straight at us from that distance, roughly once every 10,000 years. We got cosmically lucky. Or cosmically unlucky, depending on your perspective. Because here's the implication that keeps astrophysicists awake at night. If this burst had occurred within our own galaxy, say 6,000 light-years away instead of 2.4 billion, it wouldn't have just ionized our upper atmosphere. It would have stripped away the ozone layer entirely. The surface of Earth would have been bathed in lethal ultraviolet radiation for months. Mass extinction, not from an asteroid, not from a volcano, from a star dying in a galaxy arm far from our own. We've found evidence in Earth's geological record of gamma ray burst impacts. Certain mass extinctions, including the Ordovician extinction 450 million years ago, have signatures consistent with exactly this kind of event. 85% of marine species gone, from a beam of light lasting seconds. So the real question is, does this change what we think is possible for threats to life in the universe? Right now, teams across the world are in a race, not just to understand GRB 221009A, but to catch the next one as it happens. The James Webb Space Telescope has already turned toward the burst's location, analyzing the afterglow in infrared wavelengths no previous instrument could see. Researchers at NASA and ESA are building faster alert systems. When a burst happens, observatories need to pivot within seconds. Because the most valuable data comes in the first minutes, and after that, it fades forever. There's a PhD student in Italy who hasn't slept properly in months. Her job is to monitor real-time gamma ray alerts and coordinate global telescope responses. She told an interviewer, "Every time my phone buzzes at 3 a.m., I wonder if this is the one that rewrites the textbooks." The Einstein probe satellite, launched in January 2024, is specifically designed to catch these events faster than ever before. We're not waiting for the universe to surprise us again. We're building eyes specifically to watch for the next flash. So think about this. 2.4 billion years ago, before complex life existed on Earth, a star collapsed into a black hole and screamed across the cosmos. That scream traveled through space for longer than our planet has had animals. And on one ordinary October afternoon, it finally arrived, washing over our atmosphere, our satellites, our instruments, and every single one of us. We didn't feel it, but we measured it. And now we know the universe doesn't just create, it destroys on scales we're only beginning to comprehend. Here's my question for you. If a gamma ray burst could cause mass extinction with no warning, should we be building detection systems? Or is that a threat we simply accept? Follow for more, we post every week.